Hello all. This is our video about exploring the point groups. We're going to start by talking about two matrices. Matrix A, which I'll write out for you here, 0, 0, 1, 1, 0, 0, 0, 1, 0. And matrix B, which again I'll write out for you. Negative 1, 0, 0, 0, negative 1, 0, and 0, 0, 1. Now we're going to prove that both of these matrices are orthogonal. That is, that the product of the matrix and its transpose is the identity. Of course, we can just check this by directly multiplying. If I write down the matrix A, and I write down the matrix A transpose, then I can write down their product by taking dot products of rows of the first matrix and columns of the second matrix. Checking these dot products, you see that we do get the identity matrix as the product of A transpose and A. We'll write out B transpose B, but I'm going to let you actually do the matrix multiplication for homework. Be sure to also check A transpose A. Even though you've just seen me do it, it helps to do it yourself. Now here's a really cool theorem. If you have a 3 by 3 matrix, and it's orthogonal, and its determinant is +1, then it's a rotation around some axis. This is not true in higher dimensions. Now matrix A is a rotation around 1, 1, 1. You can see that actually because 1, 1, 1 is an eigenvector. So here's what it looks like. If we do A 3 times in a row, 1, 2, 3, we get back to where we started. Matrix B doesn't look much like a rotation, but in fact it's a rotation around the z-axis. Once, twice, and we're back to where we started. Now let's try it with a model. Once, twice, and we're back to where we began. Now we're going to compose A and B. When we write ABX, we first multiply by B, then A. Let's do it with the model. First B, then A. Now in fact, this amounts to a single rotation. Now we'll see it with the model. Comparing the single rotation with the sequence of rotations, we can see that in fact we get to the same place. 3 repeats of that rotation will return us to the original position. That is, AB, AB, AB is I. At this point we can ask a reasonable question. Just how many of these matrices are there? For instance, if we look at AB and BA, remember again they're read backwards, we can see that these are different elements. So how far does it go? In homework, you'll prove that you can only get 12 different orthogonal matrices by taking products of A and B. I'll call these the delightful dozen. You can prove this by taking products repeatedly, and as you do, you'll start to wonder whether you've seen a certain matrix before. For instance, you might wonder whether AABA is the same thing as BAB. We're now going to talk about 3 different ways you might try to prove such a statement, sort of in order from worst to best. The first one is simply to do it and draw the pictures. Here's a computer animation of AABAA. And here's an animation of me doing it with a physical model. A, B, A. Similarly, we can do B, then A, then B. And we can ask whether the axes end up in the same place. We'll now try it with the model. B, A, B. We're now going to look at the 2 videos together, BAB on the left and AABAA on the right. And we'll see if our model ends up in the same position and orientation. It does. To some extent, this is a proof. However, unless you're literally going to include the video, this proof boils down to saying, I thought about these 2 things, they're the same, and that's what I think. You can do the experiment yourself. It's not very satisfying. Here's another approach. We could just multiply out the matrices and see if we get the same answer. So here we go. I wrote out the matrices and I pretended to do the multiplication, which I really did with a computer. And yes, I get the same matrix as the answer. This is the method of brute force. And if we write this down in a single rotation, you can see they're the same thing. This is substantially better than the last approach because it gives you something explicit to check, even if you can't check it very easily. So now we're going to talk through an approach which I really like. Rather than just expecting people to follow along after you, or doing it by brute force, we want to give an approach that tells you why it has to be true and provides a way to check it. This kind of proof gives you insight as opposed to just verification. So here we go. Okay. So we saw before that if you repeat these rotations, you end up back at the identity matrix. If you do A, it's the same as the identity. If you do B, it's the same thing as the identity. And if you do AB, AB, it's the same thing as the identity. So let's use that last one. Multiplying by b on the right on both sides of the equation, we get AB, AB, AB times an additional b is equal to the identity matrix, times an additional b on the right. Two b's together is the identity, so we can cross those off. Now we're left with AB, AB, A equals B. Multiplying on the right by AA, we see we have three A's in a row, and we can cross them out. That leaves us with AB, AB equals B, A, A. Multiplying by two A's on the left, we see again we have three A's in a row, so we can cross them out. And we're left showing that BAB is equal to A, B, A. Now that's a proof. QED.